This video is going to seek to introduce what exactly a derivative actually is. So derivative is just our calculus fancy way of saying slope, but specifically slope at a point, an instantaneous slope. Okay, so you guys are familiar with slope with lines, right? If I give you guys, oh, here's a line, ta-da-da, and if you want to find slope for that, or average rate of change, those words mean the exact same thing. How would you find slope for a line? We would find our change in y over our change in x. Okay, and so since we have a constant change in y and a constant change in x, we have a constant slope for any line. However, if we have quadratic, polynomial, any other type of graph, whatever, okay, if I want to find a slope at a very specific point, well, if I use 2 points on that graph, then well, it might be close to the slope, but it won't necessarily be exactly the slope unless we use limits to help us make them exact. Okay, so that's what we're going to work towards coming up with a definition for. So here's some random graph, and here is an x value on that graph. Okay, well, since I want in general change in y over change in x, well, if that is x, then my y value for that would just be f of x. So I'd have the coordinate x comma f of x. Okay, well, let's use some other random coordinate on the graph. Let's use one over here. Okay, and let's call this distance between the two values h. Okay, well, if that distance is h, then if this value here is the first value is x, then this next value would be at x plus h. Okay, well, if x plus h is the x coordinate for this, well, what would I call the y coordinate? The y coordinate would be f of x plus h. Okay, so now I have 2 points. And as long as I have 2 points, I can have a change in y and a change in x. So let's go ahead and do that then. My change in y between these 2 points would be f of x plus h minus f of x. And then my change in x would be the x value for the first coordinate, x plus h, minus x. And I can simplify that a little bit to give me f of x plus h minus f of x all over, well, the x's will cancel out because I have a plus and a minus, so that leaves me with just h at the bottom. Okay, so that's all nice, fine, and dandy. When I have 2 points that are, well, relatively far away, it's easy to kind of think about that. But really, if I want my slope at a point, at x, okay, so if I want slope at x, my instantaneous slope, aka my derivative, at x, well, that means that I want these 2 points to get super, 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 super close together. Ideally, what's the spacing that I would want between these points? I would want a spacing of 0 because I want them to be so close that it defines the slope at that specific location. Well, what have we used to define the space between these points? We've used the letter h. So ideally, I want h to approach 0. Well, we've been talking the last couple weeks about this thing called a limit, right? And we can use that limit to make things really approach something. And so therefore, if I want my derivative, I'm going to want to take this limit as h is approaching 0, because that's how close I want these. I want these to be like on top of each other. Of f of x plus h minus f of x all over h. Okay, this is my first limit definition of a derivative. There is one more alternate kind of form of that definition as well, and you want to be familiar with both of them. Okay, and so for that alternate, I'm going to draw pretty much the same image, but we're going to change up how we label this a little bit. Okay, so same kind of idea. We have some image, some random graph. Okay, and I want a slope at points, let's see this one in red, at point x. Well, actually at point A. Okay, and so if we call that A, then that means the y value would be what? F of A. And so once again, to find slope, we need 2 points. So we're going to use some other coordinate on my graph, and we're going to call that point x. And so if that's x, what's the y value? F of x. Okay, and so in the same way that we did over here, we're going to go ahead and use this change in y over change in x. So that gives me change in y would be f of x minus f of a all over x minus a. Okay, and again, just like before, we want these 2 points to actually be like on top of each other. But this time we haven't defined the distance between them, we've just defined them each as their own points. So if we want the derivative at a, derivative at a, okay, then that means I'm going to want that x coordinate to get super close to a so that I have a pinpoint slope at x equals a. Okay, which means that my limit, what will my limit be? My limit will be as x is approaching a. So this is an alternate definition, and again, you want to be familiar with both of them. So this is the main definition, this is my alternate definition. So for this one, we're mostly going to be using these two definitions and using a bunch of algebra to solve our derivatives. So let's find the derivative of each of these, and I'm going to go ahead and do them using both methods so that you get to practice the algebra in both situations. Okay, so take a moment to see if you can set up this first one and then work through that problem. Okay, so for this first one, I'm going to start with using my formal definition, the limit as h is approaching 0 of f of x plus h minus f of x all over h. And so this is my f of x. If I have f of x plus h, okay, just as a quick reminder, if I gave you f of 1, what would I do to find f of 1? We would take 1 and we would plug it into the equation. Now I would get 1 squared minus 5 times 1 plus 4. Okay, so if whatever's on the inside here gets plugged in for x. So same thing here, whatever's on the inside here, that's going to get plugged in for my x's. So I'm going to have x plus h, quantity squared, minus 5 times, oh, there's another x, so I want to replace it, x plus h, and there's no more x's there. Okay, so that's my f of x plus h right there. I'm going to put brackets around that, minus f of x. F of x is just x squared minus 5x plus 4 all over h. Don't forget your limit as you work through this. H is approaching 0. Okay, so now I'm going to go ahead and do some expanding and simplifying. So I have my limit as h is approaching 0 of, let's see, this FOILed out, don't forget to FOIL, x squared plus 2xh plus h minus 5x minus 5h plus 4. And this is going to distribute. This is why it was important to put those brackets around my function so that you don't forget that distributing is necessary all over h. And that will allow me to cancel x squared, to cancel 5x, and to cancel the 4. So that leaves me with limit as h is approaching 0 of, let's see, 2xh plus h, oops, I left out a squared here, h squared minus 5h, and that's it. Everything else is gone, all over h. Okay, now what can I do? Well, I have an h in every single term up top, so I can factor that out and cancel it with the denominator. So that leaves me with 2x plus h minus 5. So I'm canceling an h from every single term here. Okay, and so now that I've simplified that, well, how do we evaluate limits again? We evaluate limits by trying to plug in. This is a 0, by the way. So what are we plugging in for? This is a limit as h is approaching 0. So do I plug in for x or for h? Well, we're going to plug in for h. So when I plug that in, h is equal to 0, so I get 2x plus 0 minus 5. So 2x would be my derivative. Okay, and this represents a derivative at any point on my graph. So for example, if I wanted the derivative specifically at, say, x equals 5, I would plug in 5 for x, and my derivative, my slope at x equals 5, would equal 10. Okay, but we'll get back to doing that a little bit later. So that's using my first version of that limit definition. And once again, I said I'm going to use both of them so that we practice the algebra on each of those and so that we get used to seeing that. Okay, being able to look at this version of the limit and recognizing it for what it is a really important skill. So we want to do that for the other version as well. So what was that other version again? We had the limit as x approaches a, in that case, of f of x minus f of a all over x minus a. Okay, so let's plug in our equations then. F of x is just x squared minus 5x, so I have the limit as x is approaching a of x squared minus 5x plus 4 minus f of a is a squared minus 5a plus 4. So again, once all I'm doing is plugging in a for all my x's over x minus a. Okay, this version does require a bit more factoring. This one over the first version that we had was required foiling, which can be tedious, and then we cancel and then just kind of do more canceling. This one is going to require factoring along the way. So I don't really care if I'm asking you to use your limit definition for something. I don't care which method you use. You just need to make sure that, you can work the algebra through it. So if you have trouble with one method or the other, you're welcome to generally stick with the one that you prefer. Maybe you prefer the first one for certain types of problems, the second one for other types of problems. So you can always change. Okay, so let's go ahead and reorganize this then to help me be able to cancel. Because again, if I want to try to evaluate this limit, if you plug in a right now, you're going to get, what's that thing called when it's 0 over 0? Indeterminate. You're going to get indeterminate. Okay, so we need to change things up. So I'm going to rewrite this. I'm going to put x squared minus a squared together. I'm going to put minus 5x plus 5a together, and the 4's cancel out. The 4's go away. I have a plus 4 and a minus 4 in there. Okay, all over x minus a. Okay, and I've rearranged it this way so that I can factor each section. I'm now going to factor by grouping. So this first part factors to x minus a, x plus a, and then the second part, I'm going to put my squiggle in here, squiggle turns into a plus. Right, my second part I can factor out a negative 5 to give me x minus a. Don't forget that when factoring by grouping, I want to make sure that there's some part that's the same in each one. Okay, so in each part I have x minus a, those are the same, so I can pull that out. So I have a limit as x is approaching a of x minus a. When I pull that out, I figure out, okay, well, what's left over? So I have x plus a left over minus 5. That's also left over. All over x minus a. And now I'm allowed to cancel this part because it's been divided out essentially. And that leaves me with limits as x is approaching a of x plus a minus 5. So once I've plugged in 0, now I'm left with 2x minus 5. Okay? This is the equation for the slope at every single point on my graph, which means if I wanted the slope at, say, x equals 1, I would plug in 1, and that would give me 2 minus 5, which would give me a slope of negative 3. So at x equals 1, I have a slope of negative 3. Or if I wanted the slope at x equals 5, I would plug in 5, and that would give me 10 minus 5, which means the slope at 5 would be 5. Okay, so this equation tells me the slope at every single point of my graph, which is pretty cool. So I said that I was going to do this using both versions of the definition. So I'm going to work through this once again with the other version so that, again, you are familiar with it. This equation right here, that first equation when we plug in, it's really important to be able to recognize that on site. Okay, and that's part of why we want to do it both ways, just so we can see what it looks like. So what is that other version of this equation, of this definition? Our other version of the definition is, is our limit as x is approaching a of f of x minus f of a all over x minus a. X minus a. Okay, so once again, we're going to go ahead and, well, throw the formulas in for f of x and f of a. So I get x squared minus 5x plus 4 as the first one, minus f of a, don't forget our limit, x approaching a, is when I just plug in a for that. So a squared minus 5a plus 4 all over x minus a. Okay, so now I want to simplify this. Let's see, when I simplify this, the 4's are going to cancel out, and I'm going to want to rewrite this so that I'm going to be able to factor, because this alternate version generally requires more factoring or more moving things around and stuff like that. Um, so we need to rearrange. Okay, so I have limit as x is approaching a of, okay, I'm going to put the x squared pieces together. So the stuff that's similar is going to all go together. Minus 5x plus 5a all over x minus a. Okay, and I'm rearranging that so that I can factor it by grouping. So by grouping, remember I'm going to put this squiggle in the middle. That squiggle is going to become a plus. And the first part is the difference of squares, so that turns into x plus a, x minus a. The second part, let's pull out a negative 5. That leaves me with the x minus a. Again, when you do this, you want to look to make sure that you have something that's the same in each term. So here I have an x minus a and an x minus a, so I can pull that out. So I have the limit as x is approaching a of, okay, when I pull out x minus a, I'm left with, or what's left over, I have x plus a minus 5 left over, all over x minus a. This now allows me to cancel, and that leaves us with the limit as x is approaching, is approaching a of x plus a minus 5 over x minus a. Oops, my bad. That part canceled out. Okay, so at this point we have now fully simplified it. There's not really much else that we can do. So how do we evaluate a limit again? Plug in. What are we plugging in for? What are we plugging into? Okay, so since x is approaching a, I'm going to plug in for x and I'm going to replace the x with a. Okay, so when I replace it with a, now I have a plus a minus 5, which gives me 2a minus 5. Okay, you may notice that that is pretty much the same equation as that one up there. It should be, right? We just did the exact same problem two different ways. It just has a different variable in it. Okay, so both of these methods will get you to the same place. Okay, so now that you have seen it done with this first problem all the way through and followed along with your puzzle, let's try it for this next one. Okay, so let's do this next one here. Go ahead and take a moment, and for each of the methods, go ahead and write out your starting equation um, with this new one. So I have 2 over x. Right, so these should be the two equations that you are starting with. Go ahead and check yours. And if it's not correct, well, make some corrections and then go ahead and work through the algebra for each one of these, and I will just kind of cast the answer up here in a moment. Alright, so here is the answer for each of them. In both cases, you did need to use our common denominators. Once you have your common denominators, we wanted to use multiplying by the reciprocal to help us get rid of that extra denominator in there. Things cancel on this side, things factor and then cancel on this other side, and then in both cases, once again, you get the same final answer just with a different variable. Right, take a look at this last one, y equals square root of x. Go ahead and again, we're going to work through this in both methods. So write out your formula, your starting formula for both of them. And then I will once again show you those answers. Right, so this is where you should be starting with each of these problems with your x plus h's and your a's and stuff like that plugged in. Once again, go ahead and make corrections if you need to, and then solve it. Alright, and here are the answers for these. Both of these did require using the conjugate on both top and bottom to help us get rid of those square roots. Remember that we are foiling in here, so I didn't write the middle terms because they end up canceling out, but we have that first, we have the outer, we have the inner, and the last. And so make sure that you are foiling for each one. Okay? Denominators I did not distribute out because there was no need to. We generally don't want to distribute out the part that doesn't use both conjugates in it. And both, again, once again, two different ways to do the same problem, so we should have the exact same answer for each one. Right, now let's take a look at some properties of our derivatives and kind of think a little bit more about what they mean. Now, let's take a moment to just remind ourselves some vocabulary. So instantaneous slope is what we are finding now, slope at a specific coordinate at a specific point versus average slope. So instantaneous slope is slope at one point, average slope is the slope that you've dealt with since Algebra 1. And that's what we use to kind of come up with our equation, right? That's my just general change of y over change in x. Whereas instantaneous slope, again, we have these limit definition versions. X approaching a of f of x minus f of a all over x minus a, or the limit as h is approaching 0, x plus h minus f of x all over h. Okay, so these are instantaneous slope equations. Average slope is the, again, average slope that you've dealt with since Algebra 1. Okay, so for this equation here, real quick, I have f of x equals x squared minus 4x minus 1. Find me the average slope on the interval from 1 to 3, and find me the instantaneous slope at x equals 1. Well, average slope, again, is just slope from Algebra 1, so I have f of 3 minus f of 1 all over 3 minus 1. Let's see, f of 3, I get 9 minus 12 minus 1. 9 minus 12 is equal to negative 4. And at 1, let's see, that's 1 minus 4 minus 1. That is also equal to negative 4. Of course, they're not always equal to the same thing, right? But in this case, they are. So I've got negative 4 minus negative 4 all over 3 minus 1, which gives me 0 over 2, or equal to 0. So my average slope between 1 and 3 is 0. Instantaneous slope, once again, that's our derivative, so we have to use one or the other of these definitions up here. I don't care which one you're using. You don't have to use both in this one, but you always can, just to kind of practice and to serve as a quick check for your answer. So take a moment to find my instantaneous slope at x equals 1. Right, I use the one using h. Okay, so here is your work for that. Again, you want to plug in that x plus h. Oops, I forgot a part over here. Minus x squared minus 4x minus 1. There we go. Doop-a-doop. That part's sometimes easy to forget. Don't forget it. Okay, and so this is your equation for my slope at any point, but remember I want my slope specifically at x equals 1. So what am I going to do? I'm going to plug in 1. So instantaneous slope at x equals 1, m at x equals 1 is, when I plug in 1, I get negative 2. All right, so let's explore some properties of slopes, or some. So let's take a look at a function and its derivative so that we can help to kind of connect this idea that one function is the slope of the other. Nope, that's still not what we're talking about. Okay. Right, so let's talk notation real quick, and then we'll take a look at some graphs of a function and their derivatives to help us kind of connect what it really means that it's a slope at every single point. Okay, so as a note, our notation for derivatives is the dx of a function. Okay, or you might say dx of f of x. Okay, this value down here, the x on the bottom, that does matter. Okay, so usually, and definitely in this class, not always in future classes, so you want to keep an eye on that, definitely in the future, but that variable tells us what we're taking the derivative over, and it should generally match the variables that are in the equation. If it's not, if it doesn't, then pretty much everything in the equation is a constant. Okay, so this is one notation for our derivative. And we can often sometimes also kind of just stuff it together. So instead of the y or the f of x kind of being on one side, we can kind of stuff it together. We most commonly see it as dy dx. We don't write it with the f of x as much. Okay, so whenever you see dy dx, if a problem says find dy dx, it's saying find me the first derivative. Okay, find me the derivative of this function. Another notation that you're going to see a lot is the prime notation. So you might see f prime of x, like that. Okay, that also means first derivative. Now, we don't always just take first derivatives. Sometimes we take higher derivatives than that. So if we take a second derivative, so take the derivative of function and then take the derivative of that, then you will see this as f double prime of x for this prime version of it. Or for this other version's a little weird to look at, so you want to get used to seeing it. If I have d dx of my derivative, okay, then once I stuff it together, notice that I have two d parts here, and I have two dx parts here, but I only have one y. So this would be written as d squared over dx squared, like this. This is how you'll mostly see it. Okay, so when you see this, that's telling you you need to take your derivative twice. Okay, so on your calculator or on Desmos, I'm going to do it in Desmos in a moment, let's graph f and f prime on the same graph. Let's go ahead and use, let's use this equation here that we had earlier. So x squared minus 5x plus 4, x squared minus 5x plus 4 was our f of x. And then our f prime, you found that earlier to be 2x minus 5. Okay, so let's graph those both on the same graph on either, again, Desmos or a calculator. So here are both of the graphs. My red graph is my quadratic, the x squared minus 5x plus 4, and the blue graph is the derivative of that. Again, it's the slope at every single point. And so what I want you to kind of, again, notice is that, well, I want to think, well, on the left side of my graph over here, all right, so here are the graphs of each one. I have my quadratic in red, that's my f of x, and I have my f prime in blue because it's linear. And so once again, I just want to emphasize that the blue represents the slope at every single point on f. So here I have a negative slope. Specifically, the negative slope is this value right here, around negative 4 point something. Okay, so the slope is negative, so the value of f prime is negative. The slope is negative, so the value of f prime is negative. And at the vertex, well, what's the slope at the vertex? The vertex slope has a slope of 0 instantaneously. Okay, and then over here, positive slope here, so positive number on f prime. Okay, now this is going to be really important for us because this is going to be how we now can identify any maximums and minimums of a graph without a calculator in the future, because we can actually use derivatives to do that for us. So what is the slope at any max or min? Okay, if I gave you some random graph, woohoo, okay, here's a maximum, here's a minimum, here's a maximum, here's a minimum. What is the slope at each of those points instantaneously? Okay, the slope at each of those points is 0. Okay, so if I want to find the max or min of any graph whatsoever, I would want to find the slope equation, the equation for the derivative, and set that equal to 0 to help me find those extrema. So let's take a moment and review kind of all of this notation that we're talking about and make sure we understand what exactly a question in function notation really means. So here I have p of t is a function representing the population of the Earth at any time t. What do each of these actually mean in context? Like, what do they mean? Well, I'm going to give you these as little multiple choice questions. So here, what does P of 2020 actually mean? Which one of these does P of 2020 mean? Yeah, well, this would just be, well, P is the function population, 2020 is my time, so that's just the population in 2020. All right, let's go to the next one. This is P of 2020 minus P of 2015. What does that actually mean? Okay, well, P of 2020 is the population in 2020. P of 2015 is the population of 2015. I'm subtracting that. So that would give me the change in population between 2015 and 2020. What about this one? P of 2020 minus P of 2015 over 5. Where does that over 5 come from? Oh, well, I could rewrite that over 5 as 2020 minus 2015. So what is this? Well, this is really just f of one thing, right? 1x minus f of some other x over the two x's subtracted. Okay, there's no limit here. So then this is just my slope equation. This is my average slope between 2 points. So that's my average growth of the population between 2015 and 2020. And this last one, that limit should give it away. With that h approaching 0, that's my instantaneous slope or instantaneous growth of the population. Oops, this should be in 2015. How do I know it's 2015? Because 2015 is what's in here. Okay, and that's my x value. So the instantaneous growth of the population in 2015. All right, so let's practice that without the context right now, but at least identifying a function. Okay, so here, the following are limit definitions of the derivative. Okay, I want to work backwards now from what we were doing earlier and identify, okay, what's the function that we're trying to take the derivative of, and at what point are we looking for the derivative? Now this first one has those h's, so this is one of that f of x plus h minus f of x all over h formula. That's the formula that we have here. Okay, so what is my function and what is the x? Well, here's my h, so this 8 is added to that, so my x must be 8. So x is equal to 8. And my function, well, remember, when I'm working forward, I take all the x's in my equation and replace it with x plus h. So to work backwards, I want to take my x plus h and replace it back with an x. So the function I'm taking the derivative of here is the equation cube root of x. Okay, so this first problem is looking for the derivative of f of x at x equals 8. Okay, well this next one doesn't have any h's, but it is still a limit definition. This is my other definition. So limit as h is, not h, x is approaching a of f of x minus f of a all over x minus a. Okay, so this one should technically be easier to find the f of x because f of x is right here. So there's my f of x right there. My function that we're trying to take a derivative of is x to the 9/2. And where are we trying to take the derivative at? This is at x equals, okay, well, where's a? A should be down here, a should be over here. Okay, so that is 1. All right, so I'm trying to find the derivative of x to the 9/2 at x equals 1. These down here are really important because I bet you don't always want to have to like work through all the algebra that we did on those prior pages. Right, right. Those are pretty long. So if you can work backwards to see, oh, if I see this equation here, I know that it's actually asking me to find the derivative of these equations here at this value there. We have shortcut methods to get there, and we will go through the shortcut methods next class, next video. Last thing I want to talk about in this video are tangent lines and normal lines. Real quick, what is a tangent line? Like, what's your definition of a tangent line? Well, tangent lines, most of you probably said, oh, a tangent line crosses or only hits the graph at one point. Okay, so here's a point. Ta-da! That only hits the graph at one point. Is that my tangent line? Most of you are probably shaking your head going, no, Miss Chen, that's not the tangent line. Okay, so other than going through one point, what else has to be true about a tangent line? Well, it has to kind of follow the graph, right? It has to be like that. Something like that would be a tangent line. Now notice that this tangent line that I'm drawing actually goes through my graph more than once. That's okay. A tangent line is not actually defined as something that only touches once. It is defined based on the point and the slope. Okay, so a tangent line must share a point and a slope at one point on my graph. Okay, so tangent line shares a point and a slope at a point on my graph. Okay, so find the tangent line of each of the following at x equals -1. You should have each of these derivatives from earlier. Right, this was the derivative for that first problem from earlier. And so again, I want it at x equals 1. Well, to find the equation of a line, I always need what? I need a point and I need a slope. Okay, so let's make sure we identify a point. Well, it gives us an x value, so how do I find a y value? Plug in. So I plug in -1, that gives me 1. Plus 5 plus 4 gives me 10. You should totally check my arithmetic, that's always the worst for me. And I need a slope. Remember that dy dx represents the slope at any point. So if I want to find my slope at -1, I just want to plug -1 into my dy dx, which gives me a slope of -7. Okay, and then I want to throw this into the equation of a line. The very best way for you to write equations of lines in this class is point-slope form. Do you remember point-slope form? Point-slope form is y minus y1 equals mx minus x1. Okay, that is the best way to write it because you are least likely to make any mistakes. If you put it in slope-intercept form or any of those other forms, if you simplify this and make a silly mistake while you're simplifying it, you would have gotten full credit by writing this right here. If you simplified it, made a mistake, you would lose a point again and you will be so sad. Okay, so no need to simplify. Just leave it like this. Okay, so that is my tangent line for the first one. Go ahead and find me the tangent line at x equals -1 for the next two. Here is that second one. My coordinate when x equal to -1 gives me -2. My slope when I plug in -1 gives me -2. So there is my point slope form of that line. Again, I'm going to leave it like that. I'm not going to change it past that. And for this last one, oh, this last one doesn't work because I can't plug -1 in here. No tangent line. So I plug in -1, I get undefined. Oops. That's okay, we don't need to find that. Okay, let's talk real quick about normal lines. Normal line, especially those of you who have taken physics or are, you may not have talked about it yet if you're in physics right now, but especially those of you who have taken physics before, you should recognize what a normal line is. What is a normal line? A normal line is another way to say perpendicular line. So this is aka also known as perpendicular. Perpendicular line. Okay, so that would give me a line that shares the point but has a perpendicular slope. Well, if I have a slope, how do I find a perpendicular slope? Okay, well that's just going to be the negative reciprocal, right? So my perpendicular line, okay, if I have a slope of -7 here, my perpendicular slope, what's my perpendicular slope? Negative reciprocal is 1/7. I'm going through the same point, so my normal lines, I'm just going to write my normal lines over here. My normal line, well, still y minus 10, same coordinate, but now my slope is y/7. Similarly for this one, find my perpendicular line. Well, my perpendicular slope would be 1/2, so I have y plus 2, 1/2, x plus 1. And those would be my normal lines. Normal, perpendicular, those mean the same things. And that's it for this particular lesson.